So here we have cling wrap, LLDPE, linear low density polyethylene, which has been pulled out of our mixed film plastic. Very, very common, but it's not just plastic, it's a combination of plastic and paper. So the paper, it doesn't melt, and then conventional plastics recycling filters molten plastic, and the paper label blocks the filters, stops the process. It takes a long time to clean it out and restart the process. So all that lost production makes it sub-economic to process the material. It's part of the explanation of why only 15% of the plastic recycled is, or 15% of the plastic that's used is actually recycled, because it's not just plastic, and it's a combination of things like paper or paper dockets left in plastic bags that block filters that help to explain it. And then there's another reason here, because how can you tell the difference between these two bits of pallet wrapping or cling wrap? And I've just selected it by colour to make it a little bit easier to understand, but the same issue does affect clear material. And this is linear low density polyethylene. It melts at 200 degrees. This is PVC film. It melts at 130 degrees. So if you actually put the two materials together in a recycling process, this one will melt first, and you've set your process for 200 degrees to melt this. This will become a gas, and that gas creates a lot of porosity in this material. Now, the chemical composition of PVC is entirely different from polyethylene. They're two very, very incompatible materials, not only because one will gas at a lower temperature than the other, but effectively a tiny amount of this PVC will contaminate a huge volume of the polyethylene, which is actually a more common material. And then you ask yourself, well, why are we using PVC film? And the answer is it has brilliant oxygen barrier properties that, if you want to keep your food lasting for longer, if you want it to stay fresh through the logistics distribution chain, if you want it to stay fresh on the retail shelf, if you want it to stay fresh in your fridge, it is actually better to use this material. I mean, what's worse, food rotting and going to landfill and becoming methane, or using a wonderfully functional plastic film? And then that tension has to be resolved in a solution for processing waste plastic that accepts that even when you look at a single thing like, wrapping for fresh food, it comes with paper and it comes with other chemically based plastics that are incredibly complex to try and reconcile. If you've got millions of tons of this material being used, and there's very, limited markets to turn this product back into new cling wrap. There's only so many sandwiches and bits and pieces of fruit or vegetable that you can wrap, and there's only perhaps so many garbage bags that you can make out of this material. So there are wonderful solutions that are called chemical recycling, where actually the plastic is broken down into its basic substance. I mean, all plastic is just a combination of carbon and hydrogen atoms linked together. If you can sort of break it down into its simple components, then you've actually got a chance to make brand new plastic of virgin quality out of this old plastic. And so this concept of chemical recycling, it's largely based on the polyolefins, which are the most common plastics out there. We're talking about not only your linear low density polyethylene cling wrap, but your low density polyethylene bread bag or frozen pea bag. We're talking about your polypropylene biscuit wrapper and biscuit tray. But the problem with chemical recycling is it can't tolerate PVC in the system. The PVC has a completely different chemical, background, and it is a contaminant that needs to be taken out. So the first step is to actually separate these two very different chemical, products, and that's where we get to a mechanical system for scale separation of plastics that look from just visual appearance quite similar. There will be clear PVC in this material. So you need to be able to separate millions of tonnes at low cost, because if it's not at low cost, then it's just cheaper to drill for oil and make virgin plastic out of oil. You've got to look at the reverse logistics costs. I mean, how do you get this material from, say, Darwin down to a facility in Melbourne? What is the cost of that per tonne versus bringing in a tanker of crude oil from Saudi Arabia? The other thing you can do with chemical recycling is actually turn this into hydrogen, and you can do that with more or less carbon dioxide emissions. The best processes will turn this into hydrogen gas and solid carbon rather than hydrogen gas and carbon dioxide. So there are emerging solutions that can give us wonderful sources of energy like hydrogen or a fully circular economy on plastic, but we've got to resolve that basic first step of separating, millions of tonnes of this mixed material, because that's how it comes. How do we know that this is PVC? Well, it sinks in water. It has a specific gravity greater than 1. And when you actually put a flame to it, it burns with a charring residue, whereas polyethylene will give you a very clean candle wax type of appearance, and also the smell of candle wax, whereas the PVC gives off a very pungent, unpleasant odour.